So let's look at an actual graph and see if we can change the binomial histogram graph into a normal distribution graph and use that as a way to determine the probability. So our question says, write the binomial probability and the normal probability for the shaded region of the graph. Find the value of each probability and compare the results. So starting out with the binomial probability, remember, the binomial probability is discrete, which means you actually have to count the items. So it's what we describe as that histogram. So look at the binomial probability. You're going to be looking at the probability of the 6, 7, and 8. So it's going to be the probability of being between 6 and 8 inclusive. So to do the binomial probability, you actually have to find the probability of the 6 plus the probability of the 7 plus the probability of 8. You actually have to do each individual one. So the way we're going to do this is using our calculator. We have a shortcut on our calculator for the binomial. Notice that our number of trials is 16, and our probability is the 0.6, the p. That's the number of successes in the trial. 60% were successful. So using our calculator, let's see, I have to probably slide this over and then get the calculator up. So remember, distributions is above vars, second distribution, and I want the binomial one. So that's that one down here, binomial PDFA. So that's binomial probability distribution function. So the number of trials was the 16, and then P was 0.6, and the X value is this. We're going to do the probability of 6, so we're using 6 there. Hit enter again. Then we're going to add to that the probability of the 7 one. So second distribution. Go back down to that binomial one. I think it's alpha A. That looks good. 16.6. And now we're going to do 7. We're going to paste that in there, hit add again, and we're going to do the 8. Second distribution. Come back down again to the binomial one. PDF. The 16, yeah, the 0.6, the 7 is now going to be an 8. And we do that one. And then we hit enter, and that gives us our answer of this. Again, usually I think they're doing the probabilities to like 4 decimal places. So we got this 0.2647, and since there's a 9 in the 5th place, that 7 has to turn into an 8. So we have 0.2648 would be our binomial probability. So I'm going to bring this back up again. Now to do the normal as an approximation, what we do is we have to now do it as a continuous. So what we pick up on, since the 6 is included and the 8 is included in our interval, again, we're making it continuous now, so no gaps, no breaks. To keep the 6 and the 8 included, you have to move to the left using the continuity correction, the 0.5. So I have to subtract 0.5 from 6. That's going to give me this 5.5. And then I have to move to the right of 8 to include the 8 in the interval. You have to add a 0.5 there. So if I add 0.5 to 8, that's going to now be 8.5. So my normal is now going to be the probability of the 5.5 as my left bound is less than x, which is less than 8.5. That's going to be our normal distribution. So remember, this is the cumulative function on our calculator. So again, if we use our calculator here, so I'm going to slide this over again. So if I do the normal distribution, so I'll go back to distribution, and number 2 is the cumulative one. Notice that we do have a lower bound, which is the 5.5. So again, we're avoiding all those z-scores and doing all that other calculations, kind of taking a shortcut here. The upper bound is to say 0.5. The mean is which we still need the mean, don't we? And the standard deviation. So I still need to do some math there for that. So pause that for a second. So our mean, if we recall, is going to be the n times the p, and then the standard deviation is going to be the square root of p times q. So I still need that math there to do this. So my mean is going to be 16 times this 0.6, and my standard deviation is going to be the square root of 16 times 0.6. And then remember, if 60% are successes, then 1 minus 0.6 would be 0.4. That would be our failures, or 40%. So I actually have to do that math as well. So I'll have to back up a little bit and do that again. So let's quit that and start that over. Oops, quit that. Okay. So we have to do 16 times 0.6 to get our actual mean for the population. So that's going to be, oops, try it again, 16 times 0.6. And that's going to be 9.6. So that's going to be the 9.6 there. And then our standard deviation is going to be the square root of, so second square root of, and then the 16 times the 0.6 times the 0.4. And that's going to be our standard deviation. And I think they usually round it to 2 decimal places. I'm going to go ahead and just round it to 3. Should be a little bit more accurate. So I'm going to have like 1.959. Actually, it's going to be 1.960. So it really doesn't really matter there. So 1.96 would be just fine as well. So now I can actually do my shortcut on my calculator. So second distributions, and then number 2 for the cumulative probability. So again, my lower bound was the 5.5. My upper bound was the 8.5. And then my mean was the 9.6. And my standard deviation is the 1.96. So it saves me having to actually calculate the z-scores and stuff. So again, notice we get, again, on this one, our probability is going to be so that's going to be 0.2691. So how would you compare those two probabilities? Are they close? Yeah, I would say they're good. So I would say the normal would be a good approximation there. So that's one of the things we kind of pick up on, is it's a lot quicker to do the normal than it is to do the binomial, especially if it gets really large. Right now we just have 3 discrete values, but it could be a lot of numbers in between there as we move forward. Okay, so I'll stop there.